So I'd like to bring up Chuck Ward, who will be talking to us from the Air Force Research Lab, and he is the lead for integrated computational materials science and engineering. So Chuck has led efforts in integrated computational science and engineering for Air Force, the co-chair for the Materials Genomes Initiative Subcommittee under the National Science and Technology Council. He is the adjunct faculty member of Materials Science and Engineering, Materials Engineering at University of Dayton. Is also the editor of TMS, Integrated Materials and Manufacturing Innovation Journal. His professional career is 30 years, 29 years, serving in several roles in research, engineering, and management. His research has focused on microstructure property relationships in titanium and titanium aluminum alloys. So he's served as a manager. He served for the Air Force Basic Research Program in metals, then as an engineer on the F-35 propulsion program, and as a staff officer to the Assistant Secretary for the Air Force for Acquisition, and then the Air Force Liaison for Materials Research and Development in Europe. So we have his PhD's in materials science. He's from Carnegie Mellon as well, and is a very active member.
Thanks very much, Renata. So what I want to talk to you about a little bit right before lunch here is, and I always love that saying, I'm standing between you and lunch, so that's usually the longest talk of the morning. So I'll try not to do that to you. So I'll talk to you a little bit about a national materials data infrastructure. So I'm going to focus on things that the federal government has been investing in for the past few years. First, I'll start talking about a little bit of policy drivers, what's driving the federal investment, some requirements from my perspective, what I'm picking up from lessons learned, some example components, collaborative environments, which we haven't talked a lot about this morning, but I think it's critical, and some of the challenges I see going forward. So there was a memo out from OSTP back in 2013 from the President's Science Advisor. They really went towards making the products of federal research freely available to the public. So one objective was get the product of research out from behind paywalls and make it available to all taxpayers. And this is something that's been going on very actively in the EU for several years as well. The other part of that, though, the interesting part, was that digitally formatted scientific data sets that support that research should also be made freely and publicly available. So that's kind of a new twist. So that's driving a lot of behavior, a lot of policy in the agencies. You'll probably all be familiar with this. That's what's driven all these data management planning requirements and proposals coming out of NSF, DOE, and soon to be DOD. So it's all talking in response to this OSTP memo about how to make your supporting scientific data publicly accessible. So that's driving an awful lot in investment as well. And then within the Materials Genome Initiative community, there's a number of federal agencies involved in the Materials Genome Initiative. You can see the blue bubbles here: MIP, DEMREF, ICMSE, CAMD, ICME. These are all the different brand names, if you will, that the different agencies have chosen to describe their Materials Genome Initiative efforts. So you won't see an MGI program per se, but you will see a DEMREF program out of NSF, for example. We established 4 strategic goals that we want to achieve through MGI. In the corner down here, you can see one of them is making digital data accessible to the community. So this is a fundamental precept of MGI that we really want to promote this, and we feel it is important to enabling discovery and development and transition of materials to the industrial base for competitiveness. So what are some of the requirements for a materials data infrastructure? First, I'll put federated in quotes. We're never going to see one giant, huge database that satisfies everyone's needs. But we do need to understand how they interoperate with each other. How do we discover data? And that, I'll talk more about that a little bit later. But this goes across government, academia, and industry. With the key ideas being they need to be accessible. These repositories need to be affordable and sustainable. We need standards for data exchange. Here I'm talking about particularly open formats, not necessarily common formats, but open formats that you can understand, build a translator for. Vocabularies, when we say Young's modulus, do we know what we mean by Young's modulus? Do we know how that Young's modulus was determined? Was it from a stress strain curve, vibrating reed, ultrasonic? That carries a lot of import to different folks, particularly in the engineering world, on how that was acquired. And then new concept for material science and engineering, ontologies. How do you start relating concepts together to make them much more machine accessible and readable, and therefore much more useful? We need to be concerned about data quality metrics, the pedigree, the provenance, verification, validation, uncertainty, quantification. The incentives associated with making data available, Bryce talked quite a bit about that, citation and attribution protocols. Clarity on intellectual property. Right now we see a lot of people just throwing up any words they want on how you can use the data. So it's all over the map. It's very difficult to reuse data when you don't have consistent application of common IP, for example, the MIT license or Creative Commons, and any potential liability that goes along with that. And last but certainly not least is knowledgeable practitioners in materials data management. I know many of you in the audience, and we keep seeing each other, and we need to broaden that audience out quite a bit. There's a concept that really came out of bioinformatics and really is being pushed by the EU. It's a nice way to frame the discussion about data and the data infrastructure, and they call it the FAIR principles. How do you make data findable, accessible, interoperable, and reusable? If you look at those four attributes of data, it's a nice guidepost to follow. There's a nice paper in Scientific Data that was just published earlier this year that walks through what it means to follow the FAIR principles. Let me talk a little bit about some of the government-funded project-based repositories. A lot of these are very difficult to find even through a Google search. And once you get to them, you can see the interfaces here. They're not necessarily machine readable. They're very valuable, nice compilations of data, but there's a lot of issues with data discoverability, machine processing, machine readability, the curation, and perhaps most importantly, the longevity. Once the grant's over, what happens to that database? Now, it's good to hear folks like Bryce saying, well, Citrine's going to ingest it and make it available, but maybe this is not the best way we go forward in the future of setting up data repositories based on projects. There is probably smarter ways to do this. One example would be under the DOE energy efficiency renewable energy projects geared towards automotive applications. They've actually, as part of their project solicitations, required that these projects, these folks are working on magnesium alloys, that they deposit their data into a NIST repository, something that's got a lot more longevity, it's a lot more centralized, has a lot of the attributes you like to see with a data repository, like assigning a persistent identifier, which helps make the data much more discoverable. So this is an example of potentially how projects could be managed into the future using more centralized databases, not project specific. We've heard a lot about the large project-based repositories. These are, in my opinion, some of the more gold standard repositories because of their size and their interface, importantly their interface. I think each of these, except perhaps Harvard, have a API associated with it. So they publish, how do I interact with the database on a machine basis? So I'm not left with just a lookup menu to try to find, hey, what's the band gap energy for this material? No, I can query the entire database to look for ranges of band gaps, for example. But these also do suffer from the problem of they're programmatically funded. So what's the long-term sustainability of these projects? They're excellent projects, they're excellent repositories, but what's the long-term future of them? We as a community need to, and government need to come to grips with what does that sustainment model look like. There are a couple agency data gateways. The DOE has a data explorer. It's pretty rudimentary, again, not machine actionable. And then NASA has one called MapDis, which is very extensive, but it's highly restricted, a lot of export control data in it. So government agencies, other than NIST, haven't been very proactive on standing up data repositories. NIST has been very good about standing up a repository based on DSpace that provides folks the ability to load in specific data sets along a number of different themes, for example, thermodynamic data. It assigns the data set with a persistent identifier, which makes it uniquely identifiable and discoverable on the internet, which is a very nice feature, but there is no API, for example, to interface with this repository. Oh, let me go back. NIST is also sponsored through University of Illinois National Center for Supercomputing Applications and the National Data Service, a materials data facility that's based on Globus technology. That's just up and running for the past few months. Doesn't have a whole lot of data in there, but it's another open, free, and accessible resource to the materials community to repose data and access it at a later time. And then you also heard about some of the activities. ASM's been in as a professional society, has been in the materials data business for quite a long time, working with Granta and now Citrine Informatics. They had a structural data demonstration project over the past year where they tried to collect everything we know about alloy 6061 and make it available to everyone. So that is out there to be used. So that's an example of a professional society playing a role as well. So let me switch gears on some of the enabling features. Maybe first a thought on standards. We often hear a lot about that in the community on standards and all. So just maybe a cautionary word that perhaps we don't get too wrapped up in that, because I know there's been, for example, some European projects that have gone on for years and years and years, tried to define a standard for mechanical property data, for example. And it's a long and drawn-out process, and I'm not sure if it's not a red herring in the conversation. Probably more useful in the short term are things that NIST is doing, for example, Materials Resource Registry, which is providing an interface with some very rudimentary interface standards on people exposing their specific resources through a central interface that NIST will maintain. And actually, the tool can be installed at a number of different sites and connected. But it will at least start giving you some very basic search capability on, hey, I know there's a database out there that contains this type of data. May not exactly give you a specific pointer to a specific data set, though, but at least it's a start. Other things the community needs to think about are the discoverability, the search. We've been doing a little bit of work on exploring semantics and ontology development and developing tools that try to link data and make it much more searchable and starting to connect concepts so you can extract not just quantitative information and data, but start gathering a little bit more information, even perhaps knowledge from literature, for example. So this is a tool that a company that normally deals in the intelligence community has now started working in materials. They've developed a tool called MapAnto. It's going to be publicly available, and again, it'll be able to be downloaded, installed, and people can connect and start interfacing that way. I think a key element that we haven't talked a lot about this morning, and I know there's some believers in the audience here, but is collaborative networks and collaborative environments. We talked a lot about getting material data out to a repository, but first that has to start locally, right? And then perhaps regionally, and then you move up to a repository. So, but you've got to make that a seamless process, a natural process at the local level. A lot of these, you see 6 of these collaborative elements, one of them here at Georgia Tech with Matt and with Surya standing up and Dave, are trying to get the arms around how do you handle the day-to-day business of materials research and collect the data. So it's not an effort when you go to publish it. It's lowering that barrier, and it's providing you a local repository that you can reuse and keep track of your own data years on out, so that a year or two from now you can reconstruct the research process for yourself. So you know that that tensile curve went with this SEM image, that went with that chemistry evaluation, and they're not all sitting in different shared folders or on a hard drive or on a DVD or in your graduate student's laptop who just left last year. So it's building that institutional, local knowledge repository that then makes the sharing of data more globally much more easy. And so there's a number of activities going on here, and I think these are critically important to the community. And then there is the publishing of materials data. And over the past just 2 or 3 years, a number of publications have started to recognize that there is value to publishing the data itself, not necessarily the conclusions or one person's interpretation. I heard a great talk the other year from a young faculty member who was looking, I think, at stage 2 work hardening rates on single crystal materials. They said, well, all these tests have been done probably decades ago, but of course people only published the reduced data. Perhaps critical resolve shear stress is a function of orientation and temperature. They didn't publish the whole curve. The data was generated, it was there to be reanalyzed, but we as material scientists only generally tend to focus in on one part of a curve, where there's a lot more information and knowledge to be gained from even a simple tensile test, let alone high energy diffraction microscopy. So there are a series of journals. Nature has stood up one specifically on scientific data. It's all-encompassing, and people are able to publish really metadata articles about unique data sets that describe how the data was acquired, how to interpret the data, how to read the files. Elsevier's got something called Data in Brief. They're generally much shorter articles. They're intended to kind of complement other journal articles. So it's an expanded experimental or method section, if you will, for a normal journal article. And then Integrating Materials and Manufacturing Innovation has also started a data descriptor article similar to scientific data, but it's going to be specifically geared towards material science and engineering. And we're looking at unique data sets where we want to try to tie together processing structure, property, performance relationships. Just a note about this one that I've got up here from Dave McDowell et al. And this is the first data descriptor article that was published. And the NIST, NSF, and AFRL ran a material science and engineering data challenge last year, where we challenged the community to use publicly available data to solve a problem, whether it's an engineering problem or a scientific problem, but it was to demonstrate the value in reuse of material science and engineering data. The winner of the challenge used this article, actually, in the data behind this article, and they were the grand prize winner, and the winner happened to be Kaladindi et al., also here at Georgia Tech, but different from the original authors, which was fantastic, but it showed the value that these articles and publishing the raw data itself can have. So some challenges. Specific to material science and engineering, we're really saddled with no single government agency has the lead for materials manufacturing. If you look at earth sciences, it's generally NASA and NOAA. Of course, the big dog on the block is National Institutes of Health. So they can do tremendous things in bio and biomedical, bioinformatics. But materials is spread across literally just about every agency of the government, so no one has the lead. So getting someone to really own the problem and take the lead is very difficult. We've already heard today a lack of data competency, data science competency in the field, so that's sorely needed. We do need open data formats, not necessarily common, but open. Do I understand? We deal with JPEG, GIF, TIFF now. Those are all standard open formats. We understand how to deal with them. So it's really a matter of, are they open? Can we understand them? That not only goes for what we publish, but what we're finding in our laboratory with something like 750 pieces of experimental equipment is trying to extract the data off the experimental equipment into a painless data workflow is extraordinarily difficult. You're dealing with unique manufacturer formats. They may not be proprietary, but they're unique. FEI and JEOL, for example, on SEM may say KV versus KEV. It's simple little things like that. But then there are the proprietary data formats, and they're a real pain to overcome if you're trying to develop a very painless data workflow to get things out to publishing into a repository. And then these collaborative platforms. Can I keep track of it? Can I keep track of the different files so that I can create a provenance for the data set? That's where the collaborative platforms, I think, really add the value, is you can start connecting the data files, often SCM, with electrical conductivity measurement. And now I establish a provenance of that entire data set. Domain vocabularies, schemata, ontologies. NIST is doing a lot of work in this area, but can we come to common terms? So when we have open data formats and someone says yield strength, we can point to something and say, yep, that's the definition of yield strength I'm using. And so that helps make machine interpretation of the data much more viable. Data management how-to resources. We've got a dearth of that in materials science. I'll talk about that in a little bit, but how do we get the word out to the community how to do this? How do we sustain the repositories and as we've heard earlier, community buy-in? So a number of other communities have taken this on with some discipline-based best practices. You see the social sciences here out of the University of Michigan. It's published a guide on data preparation and archiving. We don't have anything like that in material science and engineering. NASA's done the same thing. The earth sciences folks have been tremendous at this. People publish different formats, protocols on how to do and describe data. We as a community need to be much more accepting, if you will. We've got to get out of our science-based only publication model to how-to best practices, as other communities have done. And then at the next scale up are these discipline-based resources that are out on the web for other communities. There's the Earth Sciences Federation has got a wonderful platform that walks through how do you do data management in earth sciences? What are the best practices? What are the formats? USGS is a government agency. This is a gold standard. If you haven't seen this website, go to usgs.gov/data-management. They walk you through every step of the process of how do you acquire, how do you curate data, how do you share it. They point you to standards. It's just a tremendous resource that helps anyone figure out what's the best way to handle my geospatial data. And we have nothing like this in material science and engineering right now. And we want to get to a point where we can just point people to say, if you want to know how to do this, go here. Not just figure it out on your own. It's a pickup game like we do with a lot of other stuff, but this is the best practice. And that's how we're going to get more towards standardization. So in summary, we are creating a materials data infrastructure. Over the past 5 years since the Materials Genome Initiative, I really like Bryce's chart that showed the materials informatics taking off about 5 years ago. When we started this 5 years ago, the question was why? Why materials data? Why are we sharing this? How, what's the value in it? And with forums like this, we're moving towards why. How? How are we going to do this? What's the best practice? We still need development and application of commonly accepted standards, not necessarily standard formats, but standards on protocols, vocabularies, tools that enable these FAIR principles. We need educational resources sorely on data best practices. What are the protocols? What are formats that are available out there that folks can use? And then finally, community-wide acceptance of the benefits of the stewardship, and I think that's building. We're seeing more and more articles out there that are reusing data, that are applying informatics and showing the community what can be done and the value of data. So with that, I'll conclude, and thank you very much.